Good evening all, and welcome to tonight's TI webinar, hosted to you by Texas Instruments Australia. We are really excited to bring you extended investigations for the TI-nspire technology with the lovely Brian Lannon and the fantastic Jim Lowe. I'm sure that one of them will give me grief for saying the wrong word there, but we'll see how we go. My name is John Bayment, and I'm your host for this event, and I teach mathematics to Year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. And as I mentioned a minute ago, I am excited to introduce our first panel this evening, Mr. Brian Lannon. Good evening, Brian.
Good evening, John. I'm quite happy to be lovely. Good evening, Jim, and good evening, listeners.
Phew, I'll take that. Okay, as you can see, Brian is a very experienced teacher of mathematics and physics in a range of educational establishments. He is an equally talented TI national trainer, and I have to say, and I've said it before, but I genuinely mean it, I always learn something from Brian when he runs his workshops, and I hope I hear Tigerland tonight, not wanting to ruin his evening. So thanks, Brian, for joining us.
Very good, yellow and black.
Our second panelist this evening is Mr. Jim Lowe. Good evening, Jim.
G'day, John. How are you?
I'm just great. Thank you very much. That's great. There was a power cut here in Darwin earlier, and I was a bit worried that I may not be able to make it this evening, but you'll be glad or not glad to hear that I am here. So, yeah, as you can see, Jim is a very experienced and knowledgeable maths educator. He's always willing to support fellow teachers and trainers like myself and students in either the classroom, through QAMT, at conferences, and at UME Deadly. And how's that going, Jim?
Oh, it's full on at the moment. We're right in the middle of a fairly big project, so yeah, it's all good.
So, Brian, I'll pass over to you, and look forward to learning a bit more.
Terrific. Thanks, John, and good evening all. We've got the dream team once again. We were working together last Thursday.
Last Thursday, not a week.
Yes, Thursday last week, and we were looking at, once again, a similar topic of things that we could do during transition weeks or step-up weeks, however you, or days, however it works at your school, with TI-nspire technology. The brief for this evening, you see, is taking investigations into a more extended focus, and so we have about 3 or 4 interesting things to look at. This was the brief from last week, introductory activities. The question, and that is available if you weren't with us last week and you would like to view that. That is available in our archive of webinars on demand. The key questions that we put last week was, first of all, how do you run transition classes or a step-up program at your school, and at what stage do you introduce students to the TI-nspire technology? In answer to those things, Jim and I each shared some of the topics and ideas that we use in our school's step-up programs or have used. These are the topics that I have generally led students into during that week, and at my school we had a fairly solid 4 to 5 week program, so I think it was quite beneficial. Activities to hand to students. You've seen this many times now from the Texas Instruments Australia website. If you click on the Teachers panel and look for Australian Curriculum or Senior Inspirations, you will find menus such as this, and an activity that we highlighted last week was this one here called How Long? And the activities are such that we get that first sheet, which is the student worksheet, a second one, which is the same, but you see some red notations in there, that is the answers and notes for teachers, and also an accompanying TI-nspire file that you can download and install on student calculators as they work through the activity. I did make a note last week that I think that's a beautiful colour scheme with the yellow and black, and once again a special cheerio to our listeners from Adelaide. I'm just going to go into that activity again just briefly. The idea that we looked at last week was that if we had a 1 by 1 unit square, so 1 centimetre by 1 centimetre, and a line segment was to randomly appear in that square, how long would that segment be on average? Well, this is the sort of idea. So I'm just playing with the TNS file here. The worksheet with answers, I've got the teacher's version here, puts such questions as what could be the shortest line segment, what could be the longest of course being the full diagonal. And that's about as far as we took it last week, although we did look at using it to generate random points, for the two points in our square there, and use the calculator to determine the distance between them using our favourite distance formula, and then taking the mean of those. The worksheet goes on to the extended version that we didn't look at last week, but it said, well, okay, that's the deal for a 1 centimetre by 1 centimetre square. How would it be if we had a 1 centimetre by 1 centimetre by 1 centimetre cube? What would that look like? Or, still sticking in 2 dimensions, what would it look like if it was a 1 centimetre by 2 centimetre square? An interesting formula like this pops up. Now, I don't know that I'd necessarily be giving that to my Year 9 students, but if you're looking for an extended investigation, it's the sort of direction that we could go in. You'll see in the notes here that the author has indicated that on page 3.1 of the Inspire file, there's a function that's been defined, and you can check the average length of a line segment appearing in a rectangle that would be, say, 1 centimetre by 2 centimetres. I'll just briefly do that to show you. So here's the spreadsheet that we worked with last week, and here's page 3.1. Looks fairly empty, but this function has been defined, this D. So if I go D1, 2, it will give me the mean for a line segment appearing in a rectangle randomly of dimensions 1.2 for the rectangle. And that's our lovely result. Or, if you like to decimalize it, there's our decimal approximation, 0.8, which is consistent with what's in our notes just here. Okay, so that's taking something that we looked at last week and a step further. The notes consider extending it even further . There's the cube that I mentioned. So there's the distance between 2 points in 3-dimensional space. And whoa, we've got this z-axis appearing. And this last question, what about a 4th dimension? Well, what would that be? I guess it's time. That's what Doctor Who tells us. So what would that actually mean? If I had a line segment randomly appearing in a 1 centimetre by 1 centimetre by 1 centimetre cube, I'd need to put a unit on time as well, let's say 1 minute. So this segment was going to appear randomly and stay there for some length of time less than or equal to 1 minute. Now just think about that. It's kind of getting a little bit heavy, isn't it? It's saying how long exactly would this line segment most likely be, on average, as a mean, and on average, how long would it appear for? Now, straight away, we've taken what was a simple and easily accessible investigation into something that's rather complex, and I'm not going to try thinking about that too much more because it makes my head hurt I'm thinking about electron clouds. I'm thinking a little bit about Heisenberg's uncertainty principle. And to be honest, I'm not sure that I've ever really properly understood those things, but it can be, as we said before, a springboard to launch students into these higher levels of thinking. Okay, back to the good old yellow and black. And the next page on my PowerPoint here, that's the analysis that I found from Google for the mean length of the line just in 2 dimensions. And there's more activities. Once you've exhausted looking at Australian Curriculum Inspired and Senior Curriculum Inspirations, take a look at Learning Centre. This is a new one that's been put in, and what it's got is, at this point, 288 activities, but we're aligned to Australian curriculum. I really like this for its searchable nature. So it's from the same pull-down menu as before, but you can click on which device you're using, which will vary, of course, I understand, depending what state you're in, and what level, primary, middle, Australian senior. But did you notice this? Yep, jump back. It's jumped on me. Did you notice this? The subjects align to state curriculum. So if you're in South Australia or the Northern Territory, you can bring up the NTCE or the SACE or whichever certificate applies for your jurisdiction. Similarly, in the student resource section, we have exam preparation materials aligned to state standards and targeting the different technology that we know is being used in the different states. Okay, I did allude last week to showing another extended investigation. I talked about working out the area underneath a curve. I've got a 1 by 1 square here, and if I were to ask what's the area under this curve, before you think of integral calculus for your answer, and yes, I do show this to my calculus class, and it's a handy one for this time of year, because I can show them something that's related to what they've been doing, but it's got a different sort of a twist. I just showed that to my engineering students just this week, would you believe? Okay, so they're firmly keen on their integral calculus. Actually, I'll build it from the start. What's the area in this, under the curve in this box? Well, let's draw the box for a start. So, what am I doing here? Meant 1, of course. So here's the top of our box. Here's another side. And let's just zoom in on that. And let's put our curve in. Okay, so a Monte Carlo or a probabilistic type approach to this would be, imagine if I were to throw 100 darts, 100 random darts that would land inside this square box. Now, some would land above the curve and some below, and if I were to then count the proportion that landed below, I can work out the area of the graph, or the area of the box that's below the graph, below the curve, and of course the full box has an area of 1 square unit. So how am I going to throw these darts? Again, it's similar to our how long activity. If I pop in some spreadsheets here, and let's have an x coordinate, and let's have a y coordinate, and this is exactly what was done in the how long activity. So the command rand, a reminder, will produce numbers randomly between 0 and 1. So there's one such number. And if I copy that idea, I'll copy it across into this. It's a bit sticky on me here. So I'm going to I'll just write it in again here. Oops. The fun of holding a telephone in one hand and typing in the other. Okay, so there's our random numbers there. And I'm not sure why that's not grabbing, but I can do here we go. It's getting rather slow on me here. I'm going to jump back to the one I prepared earlier, and here we are, filled down 100 times, so I took 100 points down, and then I looked at the graph to see my points, and you can go right ahead and count them if you like. There are 100 there. But to work out the number that are below the curve, well, to be below the curve, the y-coordinate, would it not, would have to be less than the square of the x-coordinate. So in the third column, I've defined a function square, which is the square of the x-coordinate. Okay? So you can see that first one, the y-coordinate is 0.7, approximately, but the square of the x-coordinate would be 0.5. So in this case, the y-coordinate is not below the curve. The next case, it is, where the y-coordinate was, coming down here, the case down here, it is, where I've got a y-coordinate of 0.1, and yet the square of the x-coordinate was 0.8. So you can go ahead and just count all those if you like, but you can see that I've set up in the next column a test. And so the test is saying, is the y-coordinate less than the square? So in this one it is, in this one it is not. So all I need to do now is go ahead and count how many trues I see, and that's the number of points below the curve. Here's an easier way to do it. If I set up another stat graph, actually I'll just show you how that was done. Have we got a duck or something quacking in the background there? It's not at my end. It's somewhere in our webinar.
It is at my end. I was thinking how nice it was, and then thought, oh, you can hear on the webinar. Better mute my phone. So I'll leave it to you, Brian.
Ducks from Darwin can be heard as far away as Yakandanda. I've just opened up a data and stats page, and the variable I'm going to put on here is test. So there's our marks for how many points were true, that is below the curve, and how many false. And if I change that into a bar chart, I actually get a number. In this case, 32 of my points were below the graph, or 32%. So the area, given that the square was 1 square unit, the area was 0.32. Now, I know that calculus teachers were just itching to do the same thing using integral calculus, and you would get 0.33 recurring. Okay, I just think it's quite neat to be able to do these things another way. And while you're thinking about it, we could do the same sort of thing to try and work out an approximation for pi. I won't take you through this now, but I've got a circle that has a radius of 1 unit. So my first quadrant square here will have an area of 1 square unit. So once again, the area of the entire circle, of course, will be pi r squared. When r is 1, then the area of my circle will be 1 square unit. So I've got 1 square unit for the circle, pi square units, pi r squared, will be pi square units. So the area of the circle is pi. The area of a quarter of a circle will be pi on 4. So if I can work out how many points I've got in here, which I have in a similar way, you can see how I set up the formulas for this and the test, and do the similar sort of bar chart here. And I've got 79 cases, 79 points sitting inside the circle. So 79%, 0.79, and that's my approximation for pi on 4. And here it is from a calculator page. Interesting approach, just another way of doing things. Going back to that learning centre, I know Jim has taken some activities out of that. I will leave it to Jim to explain.
Jim, all yours, my friend. We can see your screen. Thank you very much.
Thank you. Yeah, as Brian said, I'm going to pick up on a few things that Brian said there and look at a couple of other activities. And the first one is one that comes up on that opening screen there, this activity called paper folding. One of the things that I like to do in this transition period is find some activities that I can expose the kids to some of the major concepts that they're going to encounter in their next year of study, and do it in a way that lets them appreciate the concept without getting bogged down too much in the theory and the technical side of things. And this paper folding one and the other activity I've picked for tonight, I think, does that. It also fits in nicely with the philosophy, I guess, of the UME Deadly Centre where I'm working at the moment, because one of the things that we advocate is that starting from a point of where the students are at in their mathematical development and looking at the new mathematics that we want to teach them and developing an abstraction process to get from where they are to where we want them to be. And that quite often involves hands-on activity and also different forms of representation and also the language that's used. So these activities and the technology that we've got here and the hands-on activities fits in nicely, and so that's why I like these particular activities. So I'm going to start up this PowerPoint properly and have a look at this paper folding activity. Now, as Brian said, these ones always have the three parts: the student activity, the teacher's version, which includes the answers, and the calculator file, which I'm going to have a look at in a moment. But again, you can just notice there this time in the additional blue writing in the teachers, how it's stressed there that students can benefit by starting this activity with actual pen and paper and folding their own sheets of paper and measuring and doing all that sort of thing so that they really understand what the problem is all about before you take them to the technology to develop the investigation further. So let's have a look on the calculator file on this. I think you can see from all the diagrams on there that it's a pretty straightforward activity to explain to kids. You're choosing a sheet of paper, you're picking the top corner and you're folding it down to touch the bottom edge of the sheet of paper. And that's cutting off a triangle there that's highlighted in yellow, and you're looking to find the area of that triangle and then go on to determine the maximum area that can be formed for that triangle. So you can see that it's suggested there that it's a Year 11 activity where I think in most states we're fairly consistent that somewhere along the line in senior mathematics of that level, they would be introduced to differential calculus and leading into optimization problems. And so if they haven't encountered it already, an investigation like this in that transition time could expose them to those concepts. And so, as I said, let's have a look at it and where's my screen gone there? Okay, so that's the activity. It's got a title page. It explains what the problem is and so on. And we'll go straight in and have a look at it. And we've got our virtual simulation, if you like, our electronic version of our paper folding. So if the students have done this already, then they should get the idea of what this thing is designed to represent. That sheet of paper folded over with the corner touching the bottom edge. Here's our triangle, and we can grab that point and move it around. And notice that the information at the top, the height here and the area is being calculated while we move the point and changing. And we've got those points appearing on the screen already. So as those points are being calculated, then tucked away here is a spreadsheet, and you notice, if you haven't seen it before, you can program it to capture the coordinates of those points. So we're capturing, if I just open that up a bit, we're capturing the height, and we are also capturing the area. And that's all set up in these files for you. So again, if you're new to the technology or your students are new to the technology during this transition period, they can just pick it up and use it and then unpack it later on as they become more comfortable with the technology. But the extra value there, the 1, simply means that this is going to happen automatically. So anytime I move these points on the diagram, they're going to be added to that spreadsheet. So if I go up here, then I'm going to get to a point where I've got no area, and likewise I can get all the way down the bottom here and get no area. And so when I go to the graph now, notice that I've put in a whole lot more points. And that's been, I won't scroll down because it's just more data, but I've got probably several hundred data points in there now captured automatically. And that's then there and available for the students to investigate. And you can see from the graph that there's quite clearly some sort of maximum value there. We've gone from a 0 to a 0, and there's a maximum in between, but it's not exactly a quadratic or any other curve that the students, I guess, might have been comfortable with up until this point in time. But it's something that they can be encouraged to work out for themselves. And that's exactly what the worksheet is designed to do. So it prompts them to determine an expression for the hypotenuse, for the hypotenuse in terms of x. So recognizing that the edge of the paper is 21 centimetres, then this bit that's folded over here must be the 21 centimetres minus this distance here that we're calling x. They then get the area, or the other side b, in terms of x, and hence calculate a formula for the area of the triangle. And then link the two things together. Okay, now at that transition point, you may not wish to talk about the derivative. That might be enough. But we're talking tonight about extended investigation, and Brian alluded to some of this earlier, and I'll just go back to my PowerPoint show. I have a little system, for want of a better name, that I use with the teachers that I'm working with in this current job to encourage them to extend investigations. And a lot of the things that I'm going to mention now have come up earlier in those that how long task, and indeed in this one. So the situation that we have is that we've got, in any sort of mathematical situation, we've got a base problem, and Our base problem was exactly that one that we just discussed, that we've got this sheet of paper, here's how we're folding it, and we want to determine the maximum area that can be formed with this triangle. And then from that base problem, it's possible to get a number of spin-off problems. So you might have a proof problem, you can read it there on the screen, a reversing problem, a special case problem, generalize the problem, or somehow extend the problem. And some of these are in fact done in the student worksheet, and you will get ideas looking back at that how long activity where particularly extending the problem has been discussed already. But anyway, let's have a look. So we know what our base problem is, so we've got the proof problem, and that's the activity as it's presented in that worksheet, the idea of getting verification somehow, getting a graph or the derivative or whatever to demonstrate that what we found is in fact the maximum area. You can reverse the problem, turn it around, give the kids a formula or a function and see if they can work out what must have been the dimensions of the paper that they started with. Take a special case. What happens if the paper is square? Does that change the formula in any way? Does it restrict the domain? Does it do anything at all? Not really in this case, but it's a question to pose to the kids. Generalize the problem. So instead of an A4 sheet, what happens if we took an A5 or an A3 or an A2 or any size piece of paper, not even restricted to the metric size, you know, size convention. And then finally, extend the problem some way. You know, what happens if we turn the page around by 90 degrees? How would that change the problem and so forth? And then, of course, you could be a little bit sneaky and say, well, any one of these, once you've done it, becomes the new base problem, and we just generate a whole series of new problems from that one and so forth. So any one of these tasks, it's always possible to extend it for those students that might just need that little extra bit of challenge or an alternative to get them along the way. The other side to this whole business of extended problems is to look at how do we set the theme for these problems. So laying the groundwork for an extended investigation. And so sometimes, again, it's necessary to come up with a situation that just allows the kids to be a little bit more hands-on. And this is one that I've used with teachers and students. This idea of we've got some fence panels. Again, in the UME Deadly Centre, we're very much focused on a real-life example. So if we're working in a rural area, it can be stock fencing. And what's the largest area that can be enclosed in that? And one of the things that we can do with that is prompt kids to extend their thinking. Quite often you will find with students and sometimes teachers is that they will restrict themselves to rectangles or quadrilaterals of some form and look at the different length sides and eventually come up with the idea that, well, we'll get the biggest area when it's a square. But you can push that and, I guess, follow that example, extend the problem, consider some special cases. What happens if instead of 4 sides we said it was 3 sides? Well, if they play around with 3 sides, they'd find they'd get the largest area with an equilateral triangle. And you can see why we picked 36, because it's got so many different factors and so on. What about if it was, well, we've done 4 sides, what about if it was 6 sides or 9 sides and 12 sides, whatever, and so on, and eventually some student will eventually come up, well, what about if it was 36 sides, each of just 1 unit long, and so forth. And you can see where we're heading with that. And so I found that a very good lead-in that we could use to this next particular task, because even students that were struggling, we could throw some manipulatives their way to play around with that. But this task, another one that's in there, take it to the limit, you can see sort of is doing exactly that. We're starting with a square, we're going to a regular pentagon, and the Inspire file is set up to let us explore that. So let's have a quick look at the Inspire file, and we'll go from our previous one to this take it to the limit. And you can see in this one that very similar to some of the activities that Brian was showing you, we use the technology to generate large amounts of data, or multiple cases, if you like. That the student workshop, if you have a look at it, will, in some of these cases, suggest that they calculate the area and perimeter of this shape manually, but we've got the scope to just change the number of sides and get this information. And notice we're keeping the same, a little bit different from my problem, we're keeping the circle constant now and varying the length of the side. We were keeping the side length constant in that previous problem, but we can get to that point, and again we're getting this idea that we're graphing these things and we're tending towards this value, a particular value, and the student worksheet does a really good job of getting the kids to consider this concept of a limit without, purely as a concept, without getting bogged down into too much detail. And it can illustrate it nicely by the other problems that we've got on here, because we can then look at the similar size figure outside, similar shape figure rather, outside the circle, and pose some questions. So will this, as an approximation to the circumference of the circle, be too big or too small? It'll be too small. Will this be too big or too small? The perimeter of that will obviously be too big. And so we've even got the idea of things converging to a limit from both sides. So really sophisticated concept, but in a way that is accessible to, I think, many, many students before they need to tackle it formally as part of that lead into calculus and so forth. And again, if we were to change some of these, I might just do that for a little while and see how many we can get. And isn't the technology wonderful, because we didn't have to do a single calculation for that, but now we've got graphs that can do that. And of course, if we change the attributes there of these dots, we'd get it a little bit finer and so on. But we can ask the students lots and lots of questions. Will this thing actually get to the limiting value, which by the time they get to this can see that it's getting very, very close to the circle. But the idea is that, well, we've got a series of straight sides, and so we'll never quite get there. So we're really hammering this concept of a limit. And I think at this stage, and that sort of investigation, I think there's a lot to be gained for students in doing that. So I particularly encourage people, if they're interested in this activity, to look at the teacher's version, because not only does it give you some of the answers, or it gives you all the answers, but if I can just find it.
But yeah, Jim, just the thought directions to be approaching limits before we talk about calculus, or as I said with my Monte Carlo one, there's another way of doing it. You don't have to use calculus.
Exactly. Yeah.
Yeah.
And I was just going to point out to the participants tonight that, you know, Peter Fox, that we're all familiar with, has written this activity, and what he's put in there is not just the answers, but suggestions as to why and what concepts you can do, and also a little bit of background knowledge about the technology. So I think that one's particularly well written. And as I said, it's a little hobby horse of mine that I love to expose students to these so-called senior concepts in a way that provides some hooks, so that when we do have to do this formally, you can say to your kids, remember when we did this activity, and they've got something that they can hook the concept onto and from their previous experience. So that's pretty much what I really wanted to emphasise today. Look, we could do lots and lots of these activities, but I really want to encourage people to get onto the Activity Centre, look in the various topics there, as we said, Maths Inspired and this Learning Centre, and find some of these things and just download them, have a look at them, and give it a go with your kids, because there's some really powerful activities in there. You know, I think if you look at what Brian and I have shown you so far tonight, we've got Monte Carlo methods. And Brian, did you do that as an option with your students? Because I think it's actually written into the current Queensland Maths B or C curriculum.
No, this was with my TAFE engineering class I was talking about. So right. I do a calculus unit with them, and their training package specifies, you know, all of what we know as the standard calculus, differential and integral. But I just think it's nice to show them another approach. We're at the stage where basically we've finished the course for the year. We're just mopping up a few things and getting ready for final assessments, and so I thought this was a good one to throw in and say, you know, you can also look at it this way. And these guys are fairly switched on. They like seeing that sort of thing.
I think Monte Carlo methods is something that it's a bit of a contradiction for students. How can we get an accurate result from doing something at random, you know? And they don't realise how powerful a technique it can be, especially when you move away from sort of standard curves and so on to something that's a little bit irregular and harder to define. But as long as you can work out which points are falling in which region, then you can get a reasonable estimate of the area. As I said, it is a part of the Queensland curriculum as it currently stands, and it's also an area where in the past we've written some code in order to generate those multiple random points and run our little Monte Carlo simulation like that. So a lovely technique, and yeah, the idea of estimating pi that way, I think is particularly useful as well. But I think, Brian, you've got something a little bit different to take us through to the end of tonight's webinar.
Yes, just another one, because I think at this time of year we can throw in a few of those little bit different things. I quite like your idea of saying, yeah, let's just put in a hook somewhere, something that when we teach the concept later on, maybe there's a reference point that we can get back to. Just pointing out, even though I haven't written the Monte Carlo up as an activity on the website, the file that I showed you, it is part of the package. So here we are, extended investigations from today. That Monte Carlo TNS file is part of the package, as also is the how long. I've tossed in a one called Introducing Sample Proportions, which I also took from that Learning Centre, which again leads on this random number generator idea. And there's another one I've put in here called Innovator Music, I'm going to get to that, but I just, there was a question that came up in the chat asking, hang on, how exactly did I get all this RAND stuff happening before I had difficulty with my calculator there? So I just thought I'd clarify that before moving on. This is the how long file with the points in. So random values for the x coordinate, y coordinate, for the first point and the second point. And then what I do in the next column is I define that column. I've given it a name for distance, and it equals the square root of, and you can see here how I've then put in x2 minus x1 plus y2 minus y, each of them being squared. When you do that, I'll just rewrite that. In fact, when I define that, I set up the square root, but to get the values, x2 minus x1, if I write x2, it's actually a spreadsheet reference. So it's easier to go to var key for the variables, and it will come up as one of the variables, which it's not going to do for me. Well, that's good, isn't it? I've upset the thing because it was defined, and I'm changing it, I think. I'll try it again from the top. Equals. Here we go, x2. So you can see the apostrophe before the x. That means it's reading it as a variable. So x2 minus the variable x1, close my brackets, and square that, and so on. I won't bore you through that. But then what I did over, I'll just cancel it. What I did over here is just in a cell here, randomly, I just put equals the mean of distance to give us the value there. In the Monte Carlo activity, I've now filled in my 100 random points. And just out of interest, if you want to regenerate those points, if you press Control and then R, they recalculate. Every time you go Control and then R, they've all recalculated. So the square that I did here was I defined that as being equal to the x-coordinate. Once again, I'm pulling it up as a variable, the x-coordinate squared. So that's the squares there. People were asking, how did I do the scatter plot? How did they appear on here? So here we are. This is the graph page, the function page. And if I go in here and on the third command, graph entry, and I go to scatter plot, it's then saying a scatter plot of what variables? Well, let's say for the x, I'm going to put the x-coordinate, and for the y, we'll put the y-coordinate, and there's those points. They come up as blobs, but we can change the attributes to make it something that's not as messy, something like that. I think is quite nice, and that's an easier representation. Okay, so as I indicated, there's another activity in the package, Innovator Music, and this is one that we dealt with in a webinar earlier on, and I thought if you're looking for investigations that really go berserk, this is just a great one. It does involve the use of the TI Innovator Hub. This is a picture of it here, and if you haven't got into that yet, I strongly recommend you do for a marginally smaller expense or an outlay for your maths department. And yes, I think it belongs in maths rather than just science. Of course, we see the overlap. I think this can really take your maths to some other great heights. These slides I've captured out of a webinar that we ran earlier. The webinar was called TI Innovator Hub, a Control Engineer's Perspective. We ran that in September. Here is the description. If you look at the speakers, we had Peter Fox, who is well known to us all, a fellow called Peter Lannon, who was the control engineer, and myself, Brian Lannon, was host. If you look at the mathematics there, we had 2 Peters and 2 Lannons, but there were only 3 people. Those of you who understand Venn diagrams may be able to see how that was so. Anyway, this is my cousin Peter. I showed him the Innovator Hub about halfway through this year. He thought it was an interesting looking device. He took it away and worked with it, and this is what he came up with. A thing called Music Player. So the variable here is the program music, and when I run this, I'm loading music from a spreadsheet. Once again, we're accessing things from that spreadsheet. 2 was representing manually. I don't really know a lot about music other than the fact that I like playing it, so I'm going to go with the spreadsheet. The transpose offset, I think, is the chord change or something to that effect. Again, I don't want to get too far into musical terms. That's not my domain. And here are our notes loading in. The tempo I do understand. 30 is a relatively slower one out of 100. And here's what we get. Okay. So I hope you appreciated that. There's the code that created that. So it's not a very big program at all. And here is the notes. And just after Peter presented us with this, there was then a member of a Google group that is discussing the uses of TI Innovator Hub, and somebody from one of our trainers from Western Australia, in fact, put up a question. There's an activity that is on the Innovator coding site that has students type in some notes to make the hub play the start of Happy Birthday, and this trainer was asking, can we do more? And there's been a massive discussion in that Google group all over the world, people throwing in their ideas and trying to get this thing to play like a piano. And it went back to Peter. Peter then came up with a spreadsheet. You can see the lists of songs here. We've got Black Dog, I've got Eleanor Rigby, what have we got? Pachelbel Cannon, and would you like it for trumpet or horn or trombone or tuba? And there's a great list here, and he's done one which was my absolute favourite, which I just think I have to share with you. And once again, I'll play it here. So when you've got something good and you just want to make it better, this is what he came up with. More notes, because it's bigger and better.
My son would definitely agree with you there, Brian.
So there we go. And I'll just show you how that can be done from the spreadsheet. Let's grab... Let's grab this one, William Tell Overture. I'm going to highlight the first column, column A, and I'm going to copy it. I'm going to go back to that program where we just heard Tigerland, and I'm going to go to the spreadsheet page, and I'm going to paste in William Tell Overture. Unfortunately, we'll overwrite my Tigerland data, but don't worry, the tigers will rise again. And I'll grab my
Brian,
second...
what if it's longer than... what if it's like short, the original was longer? Would it leave some of the bottom like Excel, or does it? You have to be careful with that?
Yeah, good question, and I wondered about that, and I even know the answer. What happened is that Peter quite cleverly put a stop point in the code, and I'll show you for our friend William Tell. Where are we? X. Can you see this cell here?
Clever.
I'll just, yeah. So as soon as the calculator reads that X, it knows it's got to the end of the story, even though there may be more notes in this particular spreadsheet. So I just thought I'd share that with you. And once again, you can watch that entire webinar if you go into our webinar archives. Whichever way you look at it, you are getting a copy of this. It'll come across, first of all, as Tigerland. I'm giving you the spreadsheet as well. So in the package here, I'm giving you this, Peter is. So this is what you get in the download. You get Peter's PowerPoint. You get the spreadsheet with all those songs. You get a couple of versions of the music player. So thank you very much, Peter, for that. And that's about all from me, John and Jim. You can see this loading on my computer now. But, John, you could take the screen back anytime you like.
What a way to take it back off you. It's like, you know, sort of teachers who ruin it for the kids and say, I've got something much more interesting, and they're going, nah, that's not much more interesting than listening to some music. So I think what's really interesting, as I hear it still in the background, that's almost as bad as my ducks or crows, whatever was outside. I think what was really interesting with all
I gave you tigers and William Tell.
What is the fact that these activities are so readily available. I love the link of doing something hands-on, you know, like the folding of the paper that Jim talks about, and saying how important that was with the technology, and the fact that they don't have to be experts with the technology. It's already on there that they can actually use. And that then combined with the ease, especially data capture or the TI Innovator Hub, then allows students to really access these activities so easily, and then to go, oh, I wonder if, and they can take it even further.
Yeah, and push the boundaries beyond just standard maths.
Yep.
Yeah.
Okay, so we are beginning to wrap things up. If you do have any last-minute questions, please try and get those asked. I know that Brian and Jim will endeavour to answer them, and they will equally add them to future planning. You can already see tonight's webinar was shaped by some comments on the last one, and Brian equally replied to some chats that were put onto our website. When you leave tonight's webinar, there will be a brief survey, which will automatically appear in your browser. And your feedback does guide us as we plan future online events. We do listen to your feedback, so we hope that you do share your thoughts in a post-webinar survey. So please take the time to do that for us. The all-important certificate of attendance will be emailed to you in the next 48 hours, along with a link. So in that, back to the other one, in that certificate will also be all the links to the documents that Jim and Brian talked about tonight. And then there will also be the on-demand and YouTube versions of the same webinar. I do highly rate those and recommend them. All of us have watched those to learn new things, especially when the Innovator Hub came out, or the iPad app, or equally now the new TI Rover, which I sent you a link to, which uses the TI Innovator Hub to drive a little car. Have you got one of those yet, Brian or Jim?
No, I'm on the waiting list there.
Right. Then you, Jim?
No, I don't have one yet. I believe early next year to get our hands on them in Australia.
Very exciting. So after we do leave tonight, if you do have any post-webinar follow-up, please feel free to phone or email us. Peter Fox and others will be on those numbers to speak to you and reply to your emails, because that's the whole point, that we're here to support you to make your teaching better and your students' understanding of mathematics and the various concepts more readily available. So that brings us to the end of tonight's webinar. Thank you so much, Brian and Jim, for everything you've shared tonight. And, of course, the participants, we really have appreciated what you've done, so thank you.
Terrific.
Thanks, John.
Thank you. And thanks, everyone, for joining us. We do hope to see you back online soon, so have a great evening and good night from us all. Thank you.